So, this is the new topic on current electricity. So far, we've been doing electrostatics. That means the charges are at rest. And then we define electric field, electric potential difference, equipotential, something like that. But all of them were just, electrostatic. So we consider charges were static, not moving. Now, on this topic, we're gonna study the current electricity, So we're gonna see what happens when charges flow. So these are the topic. It's a very small topic actually. So we're gonna define electric current, and we're gonna see the current and voltage relationship, which is called Ohm's law. We're gonna see battery EMF and power, electrical power, and finally resistivity. And then after doing this, you should be able to answer this question. What lights off the bulb? So what causes the lighting of the bulb? When you connect it to the battery. So battery has positive and negative, right? You connect to the battery, then the bulb lights up. So what causes that? So you should be able to answer the question. So first of all, the electric current is defined as the rate of flow of charge through the material, so mainly metal or resistors. So rate of flow of charge is called current, electric current. So what happens is you need a battery. Battery provides the potential difference. See, delta V is the potential difference. Battery is the source of potential difference. So when you connect the battery to the metal or any resistor, so the battery provides the potential difference between these two. So this side becomes positive, this side becomes negative, right? So positive means this is at higher potential, higher electric potential, and this side becomes lower electric potential, and that sets the electric field. See, electric field, right? That sets the electric field within the metal, and because of electric field, the electrons within the metal moves opposite to the electric field, and because we know electrons move opposite to the electric field because electrons have negative charge, and that constitutes the current. And this little animation shows that these tiny particles are the electrons, whereas these positive ions, these positive ions, right? These are positive ions, big ions. They don't move. The positive charge in solid, crystal, they do not move because they are tightly bound. Only electrons are the mobile charge carriers. Okay. And what's the electric field within the material? And it's given by our previous formula. So electric field is just the potential gradient, right? The electric field within the metal is given by this simple, this formula, right? This formula. So delta V over delta L. So delta V over the length of the metal. So, as I said, right, when electrons move, they suffer many collisions actually with the metal and with each other, with the crystal lattice. So these positive ions, these positive ions, right? These are the positive ions. Yes, when electron flows again, which is opposite to the electric field. So yeah, actually, they suffer many collisions actually per second, and that generates the heat energy. And but in all our circuit problems, we can, just consider the conventional current. So that means when you connect a battery like positive and negative, right, to the any conductor or resistor or lamp. So you can essentially you can consider the current flows from positive to negative because people didn't know that only the electrons were the mobile charge carriers by then, so people thought actually current flows from positive to negative. So it is still okay. It doesn't harm any calculations, so but that is called conventional current. So this the current flows from positive side to negative side, is just this is called conventional current, whereas the actual flow is the electron flow, right? Electron flows from negative to positive. Okay. So just keep that in mind. But in all our circuit problems later on, we're going to consider the conventional current, this positive to negative current. So comparing this current flow can be compared with the water flow. They are similar. Okay. So just like here. So what you gonna need actually in order to keep the water flowing through the pipe, right? You need a mechanical pump, right? So pump puts the pressure difference, right? Let's say positive and negative here. just like that. This represents the pressure difference, and that causes the water molecules to flow through the pipe, right? Just like that, in electricity, in electrical circuit, the battery actually works as the pump. Battery is something like electrical pump, which provides, the battery's job is to provide the electrical potential difference. This is similar to electrical pressure difference, right? And that generates the electrical current, right? This is the conventional current. So they are very similar, actually. They are very similar. So how do you know that electric current flows in a wire? And you can test in many different ways. So first of all, when you connect a wire across the battery, the current flows. When current flows, the wire gets warm, right? And you can actually this is the actual figure. Actually, this one. You can clearly see thermal energy generated. This is an infrared picture, right? And you can, if you connect the light bulb glows. So that means there's electric current, and also electrical current produces magnetic field. So if you put a little compass needle, the compass deflects. So all this proves that when you connect the wire, to the battery or capacitor, which is the source of potential difference, current flows, electrical current flows. These are the proof. So again, now mathematically, electric current is defined as delta Q over delta T, which is the rate of flow of charge. You can also say the total charge divided by T, which is also dq over dt. So electrical current is defined as, and is measured in coulombs per second, right? C over S. Coulombs per second is called ampere. So ampere is the standard unit of electric current. So, and the first law in electricity, electrical circuit, is Ohm's law. And so very simple and very effective law. So basically, Ohm's law is the relationship between current and voltage. Voltage means potential difference, right? So basically, Ohm's law states that the electrical current through any conductor is directly proportional to the potential difference across the conductor. That simply means the higher the voltage, the greater the current, the stronger the current. If you apply more voltage across the conductor or across any material, it drives more current through the conductor, and that's simply Ohm's law. So it simply says the voltage or potential difference, right, is proportional, right, is proportional to the electrical current through the circuit. And so you need some constant, right, because it's proportional, and R is called the resistance. R is the resistance. R is the resistance of the given materials, and that's caused by the electron friction, And you will see different notation. You can say delta V is IR, and you can also say V is IR. That's essentially same. V and delta V are same. Okay, so basically they represent potential difference, or you can just call the voltage. So the resistance, the origin of the resistance is of course the collisions, because when you apply potential difference, right, positive side here, and positive side here, right, and negative side here, electric field within the material is in this direction, but electron flows in this direction, right? And these electrons suffer many collisions, and that's the main origin of the resistance. And because of resistance, they generate heat, and it's enough to light up the bulb, right? So the next is, what factors control the resistance of the given materials? So here's the empirical formula. This is just the empirical formula from experimentation. The resistance of any material depends on these three quantities. One is rho. This Greek letter rho it's a material dependent quantity. Different materials have different constant. This is called resistivity of the material. Okay, it's just like density. The symbol is same, but it's quite different. It's called resistivity in electricity. Rho means resistivity of the material. It's different for different materials. L is the length of the conductor, length of the material, length of the wire. A is the area of cross section. Okay, this A is the area of cross section, which is pi r square, right? So these are some examples of resistivity. So here's the resistivity list, right, for different common materials. This is the rho. And make sure its unit is ohms times meter. Ohms meter is the standard unit. you can clearly see a vast difference of the resistivity. So for example, copper, tungsten, iron, nichrome, these are the metals, good conductors, and that means they have very little, a very small value of resistivity, right? As opposed to these are some insulators. Insulators have very high, have very high resistivity value. That means they have very big insulation, very big resistance, electrical resistance. And in general, in general, uh, the metals, all the metals obey Ohm's law. That means voltage is proportional to the current. That means you will have a straight line. If you do the IV curve measurement, current and voltage will be perfectly proportional. So that's what these are called ohmic conductors, right? Ohmic conductors are the conductors or materials those obey Ohm's law, right? But there are many other materials that do not follow, obey Ohm's law, and those are called non-ohmic. Those are called non-ohmic conductors or resistors. And many examples of filament lamp doesn't follow ohmic conductor because its resistance changes with temperature. So that's why you have non-linear behavior. This is a thermistor. This is a diode, transistors. These are semiconductor materials. So they don't obey Ohm's law. The current and voltage is not proportional. They have non-linear behavior. So these are some examples of ohmic and non-ohmic materials. So here's some more examples. So this particular device, very important, useful device, is called thermistors. Thermistors made from semiconductor materials, and that is resistance can change significantly with the increase in temperature. That's why it can be used as a heat sensor, thermal sensor. So you can clearly see as you increase the temperature, its resistance decreases. That's the properties of thermistors, and that can be used as a thermal sensor, in many applications. And here, this you will see this, in many electrical circuits. These are the fixed resistors. These are fixed. It has fixed resistance, color coded resistance. And here you will see this is also resistance, but this is a light sensing resistor. Its resistance changes with the amount of light falling on it. So that's why it can be used as a light sensor. So these are all different types of resistances examples. So next is what causes the battery to provide potential difference, the sources of charges, potential difference. So and it's because of the chemical reactions. So in a cell, in any battery, there's some chemical reactions going on inside the battery that causes the ions to repel from each other. It separates the positive charge on the one side, and that becomes positive terminal, and the negative charges to the other side that repels. The chemical reactions causes that. The chemical reactions, inside the battery causes this, these ions, positive and negative ions, to separate, and that causes and that since you have a separation of positive and negative charges within it, so that then you have potential difference, right? You have voltage, potential difference or voltage, and that's the source of any source of electric field. And if you apply if you can just connect it to the wire, it drives the current, and that's the main cause of electricity. So you can consider the battery or any voltage source, something like that. So this if you want to keep the water flow in this system, this portion is actually just lifting, right, the water up and pouring it here, and that creates the flow, electrical flow. Just like that, if you want to keep the current constant flowing through the circuit, you need a battery. Battery is just like a pump, right? Just like a mechanical. The battery does some electrical work done on the system, and that keeps the electrical current flowing through the system. And here's the next relation. So you'll hear this a lot actually. So when you have a battery, you'll hear EMF. EMF is called, is the full form of EMF is the electromotive force. So electromotive force is the maximum potential difference. It's the maximum voltage, possible voltage across the battery. The battery is supposed to provide a constant voltage, right? Battery is supposed to provide a constant voltage regardless of how much current you draw from the battery, right? But none of the batteries are ideal, and in reality, actually, the voltage across the battery decreases, almost linearly with more current. So if you put more load, if you try to draw more current right through the circuit by putting low resistance or high load, the voltage across AB, voltage across the battery decreases, and this is because of some kind of hidden internal resistance inside the battery, which is not, you can't see that, it's called internal resistance. And because of that, the voltage across the battery doesn't essentially remain constant. If you try to draw huge current, the terminal potential difference, the voltage across the battery decreases. And what's the relation? So this is the relationship between EMF of the battery, right, and the voltage across the voltage you see. So EMF of the battery, which is the maximum possible voltage the battery is supposed to give, constant voltage, right, is equal to the terminal voltage you see. This is the voltage you get. Okay, the voltage across uh, the battery plus some internal loss. This I times R is some internal loss because of this internal resistance. So the terminal voltage is always less than, less than its maximum capacity, maximum EMF, is decreased by negative. So this is the relation you might need actually in solving electrical circuit problems. Okay. So ideal battery, right? If you consider ideal battery, then its internal resistance you can consider 0 ohms. Ideal batteries, ideal voltage source has 0 internal resistance, but that's not the case, right? Okay, so these are some symbols of voltage sources. So so here's the symbol of a battery. So you can use either. So most of the time we will be using this middle one, right? So here's an example of ideal and non-ideal, voltage sources or batteries. So this is the first one is the ideal voltage source. So ideal voltage source means it is supposed to provide a constant voltage, right? No matter what resistance you put, what load you put here across the battery, no matter what actually current you draw, it's supposed to provide a constant output voltage across AB. But like I said in the previous page, it's not going to happen right? Because any battery has some internal resistance, which is in series. This RS is just the small r, which is the internal resistance of the battery. Because of this internal resistance, the voltage across the battery actually decreases with increase of current. If you try to draw more current, you're not going to get the battery voltage that you expect. So it will decrease linearly like this, right? And that's because of this internal resistance. And this is called non-ideal practical voltage source. You can also call non-ideal or practical voltage source. This one is the ideal one. So here's the main difference between EMF and potential difference. EMF is the maximum potential, constant potential difference, right, across the battery, which you can get. The potential difference is the difference of electric potential between any 2 points closed circuit, right? It is independent of the resistance of the circuit. It depends, right? And just try to read that. So the last one is energy and power. Okay. So if you have a battery, so here's the battery, right? You connect a lamp or any load resistor, right, like this. So yeah, then you have a conventional current, I, right? So the battery, what's the battery power? Battery power is, in general, power is energy over time, delta U over delta T. Delta U is the energy. So what is energy? Energy is Q times E, right? E is the electric field. E is the voltage, right? It's the EMF. This is not electric field, it's the EMF, right? From our previous slides. So the battery power is defined as the energy per time. But what is energy? Energy is the charge, this little charge flows, right, times charge times the voltage, charge times this is the EMF. The battery has this EMF, right? Suppose this is an ideal battery, and EMF is the voltage. So charge times voltage is the potential energy. This is the energy. But delta Q over delta T is what? Delta Q over delta T is current. So you can say the battery power, the maximum, right? The maximum power that the battery can deliver is equal to I times is EMF, and EMF is nothing, is just the voltage, the maximum possible voltage, right? So this is the maximum electrical power that the battery can deliver. So just current times voltage, current times is EMF, right? So so similarly, the power dissipated in the resistor is I times V, where V is the potential difference across the resistor. This is V of R, right? So in general, you can say in general, power, the electrical power is just current times voltage across the resistor. Okay, it's that simple. Okay, so in general, electrical power is just the current times voltage. Okay, and it can have many different formulas. But the first formula is, as we discussed, power is just current times voltage, right? But since from Ohm's law V is I times R, now you can express power in terms of current and resistance, because if you put V as IR, so you get second form of the power, electrical power is I square R. And you can have a third form, because I is V over R, so in terms of voltage and resistance, this is the third formula. So you can either use electrical power as I times V, or I square R, or V square over R, depending on the situation and problems. You can use one of them. So here's some conceptual stuff. In any power, electrical power transmission, the electrical power transmission is, once the power is generated here using, it could be hydroelectric power, it could be nuclear, it could be thermal. Any generated power is transmitted, through a long distance using this national grid, with very high voltage. Any generated electric power must be transmitted with a very high voltage, right? Thousands of volts, right? And using that is done by step up transformer, and the mainly because to reduce the ohmic loss. Okay, the generated power is transmitted through at very high voltage, mainly to reduce the heat dissipation. Mainly to reduce the loss of heat. And it's called ohmic loss. Because if you don't transmit the electrical power with high voltage, most of the power will be lost during transmission through the national grid, because you have to reduce the current. So that's why you have to increase the voltage. That's the main reason. And here's some understanding. So these are some short questions you can answer, right? So for example, so if you buy a heating coil, say if you are designing some heating coil, if you buy a heating coil, you need to check this specific manufacturer specification. So what does it mean? So what does this 115 volt 14 amps heating coil mean? So that simply means you can have many different information here. So this V is, that means if you put 115 volt, right, that simply means if you put 115 volts, how much current you get? You're gonna get 14 amps of current. So you can right away you can calculate the resistance of this coil, right? Resistance of this coil, which is V over I. So it's 115 volt divided by 14, right? Something like, and then also once you have R, you can calculate the power dissipation, right? Something like that. So this manufacturer's specification is very important. And these are some photoresistor, as you know. And here's some other as examples. A set of light bulbs have different rated voltage and power, as shown in the room. Which one has the highest resistance? So I'm just gonna give you hints. So you have voltage and you have watt means power. It has to do watt means power, right? This is the electrical power, and it's acting which one has the highest resistance. So use this, P is V square over R. Okay, use this formula. So since P is V square over R, R is V square over P. Okay, and figure out which one has the highest resistance. And these are some, after that, there are some examples problems which I have made a separate video.